Howdy, everyone. Happy Wednesday and happy St. Patrick's Day. I think most of us probably don't know who St. Patrick is, but we know it's got something to do with the Irish. Uh, just out of curiosity, let me ask you a question, which please reply on chat. What do you think the population of Ireland is? And second question is, how many Irish Americans there are? So send me some quick answers. So let's see what we get. Okay, well, a lot of people are right on track. Some people are way off. The latest population that the internet told me it's 4.9 million. Now let's see what the other question is. How many Irish Americans do you think there are? Some people say way more Irish Americans. I have a number of 15 million, 5 million. The number is, I think, 53 million Irish Americans, and there's still only not quite 5 million people in Ireland themselves. Okay, one more quick Irish question. What fraction of the Irish people have red hair? Most of us believe that red-haired people come from Ireland. What percentage do you think have red hair? I'm seeing 100%, 50%, 30%, et cetera, et cetera. The answer is 3 to 4%. So most people in Ireland have black hair. I've been there once and I can confirm that you don't see all that many red-haired people. On the other hand, if you see somebody with red hair, there's a good chance they may be from Ireland. Last thing about the Irish, I've been to Ireland once, and the Irish, of course, are famous for their limericks. So I'm going to read you a limerick. There was an old man with a beard who said, "It's just as I feared. 2 owls and a hen, 4 larks and a wren have all built their nests in my beard." So there are a lot of nice modern limericks having to do with Darth Vader and so on. So if you want to hear these, they all have the nice, cute little rhythm that we have. Okay, so last comment before we get on. I'm showing this slide with Heisenberg being bemused or amused or discouraged. Most people still think that atoms look like this on the left, and hopefully after we've done our first section on quantum mechanics, we now all realize the electrons cause a probability distribution that look more than that. There's a few more chats coming in. Okay, somebody said, people are talking about dying it, misspelling die, D-I-E, but anyway, many of the red-haired people do come from Ireland. Okay, a week from today, we will have a review for our second exam, and the exam will be the Monday after that. I sent you an exam review. The exam review is a little bit skimpy on the spectroscopy of diatomic molecules, but there's a lot of that stuff in your lecture notes, and I'll go over some of that today, and we'll also go over some of that next Wednesday when we do that. Okay, so as I said last time, we're to the part that often gives people the most trouble having to do with diatomic molecules. You can pretty easily learn about pure rotational spectra. You can also learn about vibrations. Here are the vibrational quantum states. But what happens is that each of these vibrational quantum states also has rotational quantum states. And when you look at vapor phase molecules, which are capable of rotating, then you find that the spectroscopy of vibrations always involves changes in rotational energy also. So we come up with these diagrams. Down here, these are pure rotational levels. It says quantum number V equal to 0, which means the vibrational state is not excited. We go up here, this is quantum state V equal to 1, the first excited vibrational state. For HEL, it's 2886 above the ground state. For carbon monoxide, it's something like 2200 wave numbers above the ground state. But the transitions that you see in absorption are those shown here. Delta J has to be either +1 or -1. And then they're called either R bands or P bands. So on the right side of the diagram, these are the R transitions, J going from 0 to 1, or 1 to 2, or 2 to 3, or 3 to 4. In all cases, quantum number V goes from 0 to 1. You can also have the P branches going from 1 to 0, 2 to 1, and so on. And we have a chat question. The lower part, J0 to 6, these are these are all rotational levels. The transitions I'm showing are called rotational vibrational bands because they go from rotational levels to combinations of rotational levels and the first excited vibrational state. So this is what you see in absorption. In Raman spectra, you can see delta J0. So you can go J0 to 0, 1 to 1, 2 to 2, etc. All of these fall almost exactly at the same frequency. And then you can have delta J equal to +2, 0 to 2, 1 to 3, 2 to 4, and so on. Or you can go 2 to 0, 3 to 1, 4 to 2, and so on. Okay, there's a question, how do they change for Raman? And the question was asked just before I showed that. So the right side here, these are the Raman transitions. I'll go over these again later in today's lecture, but here I'm just presenting it for you. Okay, some things to point out. Higher J values, as you remember, mean faster rotation. Higher quantum number V values mean faster vibrations. This is little v, the vibrational quantum number. So what kind of frequencies do you expect? We might look at the P4 band, either the subscript or the value in parentheses indicates the J that it starts from. So J goes from 4 to 3 for a P branch. Delta J is equal to -1. V will go from 0 to 1. HCl has a vibrational frequency of 2886. I should have probably put a decimal point on it, but let's say it's 2886.0. To know where this transition is, we calculate the energy of the state we're going to. And so the final state will have energy J times J plus 1, or 3 times 4. And then you multiply times B, the rotational constant. So if you've forgotten, look up the formula for rotational energy level. So this is the state we wind up at. And then this is the state we start from. J times J plus 1. We start at 4. So J is 4. 4 times 5 times 10.6. When you work this out, then you get about 801.2 wave number. So that's where you expect the P4 band. If we want to calculate a Raman band, S2, that'd be J2 to 4. S means delta J is plus 2. Vibrational quantum number in all these cases goes from 0 to 1. And so our increase in energy winds up being 14 times B. We go to 4 times 5 or 20B. We start from 2 times 3 or 6B. So we increase the rotational energy by this product right here. So in all of these cases, we have the change of vibrational frequency, but then we either gain or lose energy in the rotations. And I showed you the spectrum last time of carbon monoxide. This is in the absorption realm, so more absorbance when we go up. There's a gap in the center in infrared spectroscopy because you don't see delta J0. And then on the high frequency side, which goes to the right here, all of these levels are separated by 2 times B, the rotational constant. You remember in the purely rotational spectra, where we stay at quantum number V for vibration equal to 0, and we only have rotational changes, the bands are also separated by 2 times B. The vibrational frequency in this case, of course, is just exactly halfway between the P1 and the R0 band. On the right, these are delta J plus 1, R bands. On the left, delta J minus 1, or P bands. Okay, so the next section I put in your notes, this is all pretty much repetition of what we're talked about. But since this last part about vibrational rotational spectra can get a little bit confusing, I just want to kind of summarize and look at everything again. So the next few pages are a summary. So we use our harmonic oscillator model to represent vibrations. We say our potential energy is 1/2 kq squared or 1/2 kx squared. Here I'm using q as our coordinate, as our displacement from equilibrium. So if masses m1 and m2 are at x1 and x2, if you take their difference, then that's going to give you the value of q. I'll show you this just in a little bit, but technically the force constant, which is also called the spring constant, is really the second derivative of the potential energy taken with respect to the coordinate squared. So I'll look at that on the next page again. We solve the Schrodinger equation. We stick in capital B here, 1/2 kq squared. We're seeing the solutions come out looking like this. If we write it like this, if we want capital E to be in joules in energy, and if we wanted to go into wave numbers, we have to solve for the vibrational frequency in seconds to the -1, divide by C, and we get our vibrational frequency in centimeters to the -1, which is what we typically use. The harmonic oscillator model tells us all these separations are h nu vibrational. We're left with a 0-point energy, 1/2 h nu vibrational. And so you can see, according to the harmonic oscillator, the 0 point is exactly 1/2 of the vibrational frequency. Each of these separations is just the vibrational frequency, basically. If I multiply it by h, then I get the energy in joules. But if you take half of that frequency, you get the 0-point energy. Harmonic oscillator says delta V should be ±1. That's either for infrared or Raman spectroscopy. So we should not see overtones like 0 to 2, 0 to 3. But as I said last time, because of the anharmonicity, that the harmonic oscillator is imperfect, we can see those overtones as maybe 5% of the regular bands. IR requires dipole moment change, and so you cannot see spectra of diatomics like N2 and O2 and H2 in infrared spectroscopy. In Raman spectroscopy, you have to have a polarizability change. That basically means the shape of the molecule has to change during the vibration. now all diatomics can be seen in Raman spectroscopy. And so whatever information we want to get on H2 and N2 and so on, Raman is the way to get it. Okay, so if we get a vibrational frequency for HCl 2886, and we want to know what the force constant is, here's an example calculation. We first are going to need to calculate the reduced mass. Reduced mass is the product of the masses divided by the sum of the masses. And you then get the answer in atomic units. If we want to get it into grams, we divide by Avogadro's number. Usually in my notes, I'll call Avogadro's number N subscript AVO to make it clear. In a lot of textbooks, people put in a capital L for Avogadro's number. So you'll remember from freshman chemistry, if you take an Avogadro's number of a molecule and its molecular weight is, say, 16, Avogadro's number will weigh 16 grams. So the way you convert from atomic units to grams is you simply divide by Avogadro's number, and that's what I've done here. So again, we're going to want to work with grams when we do reduced mass, because we want to work with centimeters to the -1 when we put in vibrational frequency. Okay, well, if you plug all of these numbers in, 2886 for the vibrational frequency, mu to be this value right here, speed of light, you multiply it out, the answer will come out 4.8 times 10 to the 5th dynes per centimeter. So a dyne is a small Newton. I think it's 10 to the 7th dynes per meter that comes out. Okay, right here, then this is the units that your book would use. A Newton per meter is 100 times greater than the dynes per centimeter. If you take off the 10 to the 5th. The units I told you about last time are millidynes per angstrom. So if you want to just drop the 10 to the 5th, you just write 4.8, and it's millidynes per angstrom. An angstrom you should have run into, but if not, it's 10 to the -8 centimeters. Okay, so this is a typical kind of calculation you might have to do on your second examination. We've also talked about anharmonicity. And so I pointed out that this is not a parabola for the real curve. If you try to vibrate the molecule and you make the bond distance too large, as we go here, so Q going to the right means the bond distance is increasing. At some point, the two atoms fall apart and go into separate atoms, and they call this at the dissociation point. So the energy from the bottom of this potential energy curve to the dissociation limit is called D sub E. Last time I also pointed out there's a D sub 0. If you start from the lowest vibrational state, D0, and go to the dissociation limit, that's how much energy you actually have to put in to dissociate a molecule. And that's called D0. Many people who like to talk about anharmonic oscillators like to expand this in a Taylor series. You would have seen something like this in your calculus course. You have a constant, then first derivative evaluated at the energy minimum times the coordinate, then the second derivative evaluated at the energy minimum, and each term has a 1 over n factorial on it. So the q squared term has a 2 factorial. The third term that would come out of it is 1 over 3 factorial, third derivative of dq3, q3, and q cubed. So a lot of people may look at a more accurate model of vibrations like this. But my main reason for showing you this is how we get to the harmonic oscillator model. We basically know that the potential energy at the energy minimum is going to be 0. So this second term goes to 0. First derivatives at energy maxima or minima are 0. We arbitrarily, but always, set the potential energy constant to be 0 at the bottom of the curve. And so these first two terms drop out. And you see then, if we define this second derivative with respect to q squared as k, then this becomes 1/2 kq squared. And that's the harmonic oscillator law. So that's what I've written here. So we're not really dependent on our physicist friends to tell us that we have to treat the molecule as a spring, or having the bonds be like springs. We can get it straight out of the Taylor series. And if you go further, then the next term would look like this. It'd be the third derivative evaluated at the energy minimum. And that would be the anharmonicity constant that you would get out of this kind of expression. Okay, so we can pretty much ignore this next part here, but if you go to your textbook, you'll talk about anharmonicity constants, which going way back historically, I think your book copied the convention. It's written as omega E xe with a bar over it, and it's just one value. It looks like a product of two things. And your book also talks about omega E, the harmonic frequency, which is not the observed frequency. So it's going to turn out that the energy levels, according to this scheme, wind up looking like that. So even though for HCl, the real vibrational frequency is 2886, omega E, that your book will tell you, is 2988.9. So this is not the real experimental value, but you get the experimental value by taking 2 times this constant here, omega E xe, subtracting from that, and you get the observed frequency. Okay, so I'm telling you that just perhaps to help you avoid some confusion with the book, but in fact, it may add more to it. As far as anharmonicity goes, we're not going to do any calculations with that. I could ask you a concept question about anharmonicity, why it's there, but there won't be anything quantitative. Okay, so those are the vibrational levels, and here's a reminder about a rigid rotor rotation. Again, we start off with the fact that rotations are 100 times slower than vibrations. So a molecule will have vibrated 100 times by the time this molecule rotates all the way around. So that makes it feasible to assume that we just have a fixed bond, because the rotor is just going to see an average value of the bond distance. And we go through the mathematics from there. And we did that before. We came up with the fact that energy levels could be written in terms of moment of inertia. And from that, we defined a rotational constant. So here's a reminder about rotational levels. These are called pure rotational levels. J can be 0, 1, 2, 3. The energy levels are given by B times J plus 1. So the first level is 1 times 2B. The next level is 2 times 3B. The next level is 3 times 4B. Next one will be 4 times 5B or 20B. And the transitions we see in infrared spectra then are delta J plus or minus 1. The minus would mean emission, but very few people really look at that. We also have to have a permanent dipole moment in the molecule. So we can see 0 to 1, which in HCl is at about 21 wave numbers. Then 1 to 2 is at about 42. 2 to 3 is at about 63 wave numbers. They all increase by 2B values. In Raman spectra, I'm not showing it on the diagram, but delta J is equal to plus or minus 2. So the first transition would be from 0 to 6B. The next transition would be 2B to 12B or 10B. And so this is what your spectrum looks like. I mentioned that in Raman spectra, we also get anti-Stokes bands. We typically ignore these. These are transitions that start from the higher level and go to a lower level. So the minus 6B would start from J equal to 2 and come back to j equal to 0. The ones we normally look at start from j0 and go to 2. Notice again, there is no change in vibrational energy. So these are called pure rotational transitions. And now we're back to the same energy diagram I was showing you before. These are strictly the infrared transitions. So quantum number B is on top, equal to 1. Here in the bottom, it's 0. So the lowest rotational level here, up to the lowest rotational level there, the difference is exactly the vibrational frequency, which for HCl is 2886. On the right are R bands. So the first transition goes from J0 to J1. So you can see the frequency is nu naught plus 2B. So for HCl, it would be 2886 plus 2 times the rotational constant, and you get to something like 3007 Way numbers. And then each of these bands will increase yet by another 2B. First one is plus 2B, then plus 4B, plus 6B, and so on. And then on the left, you lose rotational energy. You start from 2B, go to 0. You start from 6B, you go to 2B, so you've lost 4B, and so on. So that helps understand then why you get a spectrum like this. So here's an actual spectrum of HBr. I didn't pick HCl because HCl has isotopic species 35 and 37, and that clutters the spectrum somewhat. And HBr, it's got 2 isotopes, 79 and 81, but they're so close together that the vibrational frequency just comes out basically in the same place. Okay, so notice in this spectrum, you always have to be careful which way it is. The energy and vibrational frequency increase to the left. So the R bands are over here. So 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and so on. On the right side, these are the losses of energy. So we go from 1 to 0, 2 to 1, 3 to 2, 4 to 3, and so on. But in all these cases, the separation is 2 times B. If you want to know the vibrational frequency, you can take the average or the exact midpoint of these first 2 transitions. This is the R0 band, this is the P1 band. And so that's where the vibrational frequency comes. Now, the type of problem that I might give you on your second exam is just like this. Find the bond length from the spectrum that is up above, and we'll just go through the calculation here. We can also do the force constant calculation, but first, let's calculate the bond distance for HBr. So excuse me, I haven't written out the actual wave number values here, but if you take the separation between any of these 2 bands, you find that the spacing is 16.95 centimeters to the minus 1. No, still doesn't come on the screen for the centimeters to the minus 1. So if we know the rotational constant from this, we take 16.95, divide by 2. We know it's equal to this quantity. And as I promised you on your exam, I will give you this formula. You don't have to memorize this number. It's something I always remember because I use it quite often. But if you put in 28.0 times 10 to the minus 40th in the numerator, then the rotational constant is equal to that divided by I. And of course, then I can just rearrange it and have I equal to 28 divided by 8.47 and get 3.31 times 10 to the minus 40th. And the answer will come out always in gram centimeters squared. Now we need the reduced mass again. We've just done this calculation up above, but let's do it for HBr. Bromine has a mass of 80. I left off the decimal places. So the product of the masses, 1 times 80 is 80, divided by the sum of the masses, 81. We divide by Avogadro's number, and this is the reduced mass for HBr. So we see from here, the bond distance squared will just be I over mu, and we get that, take the square root. And so if your freshman chemistry book told you that the bond distance was 1.42 angstroms from HBr, this is precisely the calculation that it came from. It could have come from the pure rotational spectrum also, but in this example, you can see we can simply get it from the spectrum near 2,500 wave numbers here. So that's 2,500, 2,600 wave numbers. So notice the HBr's vibrational frequency is about 300 wave numbers lower than HCl, and its force constant comes out lower also as a result. I think I showed you this last time. This is an example of a pure rotational spectrum. I think this is carbon monoxide again. If you start from lower states, then these are delta J equal +2 transitions, and you get so-called Stokes lines where the Raman frequency is decreased by whatever level you wind up on. If you start from upper states and go down, then you get an increase in the overall laser frequency that you put into your system. Okay, and I showed you this last time too. Then this is the mid-Raman spectrum of carbon monoxide. Delta J is equal to +2. So here's the Q branch. Delta J can be 0, so there's no rotational change in this band. You can see this is a lot more intense because there's a lot of the transitions, 0 to 0, 1 to 1, 2 to 2, 3 to 3. All of these other bands come from just one individual Raman transition. You might also notice a little bit of width to the central band, and that's because by the time you get to the J equal 15, the J equal 15 transition, that is not precisely the same as 0 to 0. So there's very slight shifting as you go to upper J levels. But for our purposes, we'll say it's always the same. Okay, so that's a pretty good summary of what you can expect on questions on the exam for diatomic molecules. If you look in your notes, you'll see the practice problems. This is on rotations and vibrations of diatomics, and there's answers given for that. So make sure you study those. Here is another problem. This has some vibrational parts, but it also asks you to write the molecular orbital diagrams. You remember we did these for diatomic molecules. And here's some more calculation of vibrational frequencies. So answers related to it. This is related to the Alfov scheme that we have for it. Here's an HCl spectrum with labels, some transitions shown. And then there's some practice problems, Hückel type problems that you have. So you have lots and lots of these problems to practice and get ready for the second examination. Okay, so most molecules, of course, are not diatomic, and so we naturally want to look and see what happens when you put more than one bond in a molecule. And so we'll now move on to polyatomic molecules. And so the rest of today, Friday and next Monday, we'll talk about polyatomic molecules, and wherever we stop, that's as far as will be on the second examination. So there will be a little bit on polyatomic molecules. You may have had this discussion in freshman chemistry, or maybe even in freshman physics. It takes 3 degrees of freedom to describe the motion of a single body. So we need X, Y, and Z coordinates to define where something is or where something has gone to. So if you have more than one atom, and let's say there are n atoms, you're going to have 3n degrees of freedom. In our example here, for a diatomic molecule, n is equal to 2. We have 2 atoms, so it takes 6 coordinates, x1, y1, z1, x2, y2, z2, define the 2 atoms that we have. For those 6 degrees of freedom, we can define 3 translations, the entire molecule with both atoms going the same amount in a particular direction, x, y, or z, or any combination of those. It doesn't have to be exactly along x, y, or z, but anything we can represent in 3-coordinate space. Now, the unusual part about diatomic molecules is they only have 2 rotations. And so I've shown these here. So see the dotted lines? We can rotate about those axes. So we can have the rotation about this way, or if we put a dotted line perpendicular to that, then we can rotate in the plane of the screen and have a rotation that way. So there are 2 rotations. And as you can see, the moment of inertia for each would be the same. The center of gravity is in the same place, and the moment of inertia, mu r squared, comes out to be exactly the same, whichever axis we choose. We do not have a third axis of rotation, because if we put an axis along the bonding axis, the atoms are exactly on that axis. So the definition of the moment of inertia, mu r squared, it comes out 0, because r, the distance from that axis, is 0. So a diatomic molecule has only 2 rotations. So we've already been talking about vibrations of a diatomic molecule, so it's a good thing. We're left with 1 degree of freedom, and that's a vibration that we have. It turns out this is the same for molecules like HCN or carbon dioxide, OCO. Those are linear molecules. They also lack one of these rotations in their degrees of freedom, and so they have 3n minus 5 vibrations. If the molecule is not linear, it's going to have 3n minus 6 vibrations. So benzene has 12 atoms, so you get 3 times 12, 36 minus 6, it's going to have 30 vibrations in the molecule. Some of them are going to be degenerate at the same frequency in pairs, but there'll be a total of 30 vibrations. Now, I apologize for what I have next. I have a mistake here, and I'll correct it as we go, but I haven't been able to, again, get back to my office to do this. Let's take ethane as an example. This has 8 atoms. So it has 3 times 8, 24 degrees of freedom. We subtract 6 for the translations and 3 rotations that polyatomic molecules have. So we're left with 18 vibrations. We're not going to analyze the molecule right now, but what we're going to wind up with are 6 carbon-hydrogen bond stretching vibrations, and they're mostly going to be at different frequencies. And what I left out was there's also 1 carbon-carbon bond stretching vibration. So please write that into your notes. 6 CH stretches, 1 carbon-carbon stretching vibration. And if I had remembered that when I made up the notes, I would say there are 11 other types of vibrations which are different angle bendings. Many people who only get through organic chemistry are left with the impression that almost all vibrations involve stretching of bonds. But for larger molecules, most of the vibrations involve angle bendings or torsions or twists or wags and various kinds of wobbles that molecules are doing. And I'm going to have an opportunity to show you what some of those things are. Uh, Something you would have no doubt learned in organic chemistry is that you can look at parts of molecules, especially organic molecules, and be able to tell what some of the components are. So there are what are called functional group frequencies. CH stretches, for example, typically occur in the 2900 or 3100 wave number range. And you can even fine tune that. If you have a CH stretch on a benzene ring, it's on the upper end, maybe on the upper end, maybe 3100. If you have an alkane, it might be 2880. If you have an olefin, it might be around 3000. So you can fine tune a lot of these spacings that you have for molecules. But here I'm pretending you could have a molecule that looks like this. So if you had this, you'd expect to see bands here. If you had a ketone or an aldehyde, carbon-oxygen double bond stretches are about 1700 wave numbers. If we had a carbon-carbon double bond, which I don't have up here, it would have a band around 1650. In infrared, these are usually very weak because there's not much of a dipole moment change. If you have silicon hydrogen stretches, as we found in a lot of molecules that were prepared in my own laboratory, they're easily identifiable at 2150. Whenever we try to synthesize a molecule and we didn't see this, we knew we failed. Typically, we'd see a band about 1050 wave numbers, which was characteristic of a silicon oxygen stretch. That meant our molecule got exposed to air and got oxidized and our synthesis failed. So these functional group frequencies can be very useful very quickly to tell you if you have certain components in molecules. In these larger molecules, if you observe some of these frequencies, you can also pretend that they're sort of like diatomic molecules, and you can calculate individual force constants, for example, for the silicon hydrogen stretch. So if I have, say, dimethyl silane, and I have a silicon hydrogen frequency, I can calculate a force constant. Maybe I substitute it with diphenyl silane. I can see what the effect of the phenyl ring is in the silicon hydrogen bands, and I can tell whether the bond is getting stronger or weaker based on its force constant calculation. So these are called group frequencies, and you can treat these parts of molecules as if they were diatomic molecules. The thing that makes vibrational spectroscopy of polyatomic molecules quite complicated is that most vibrations at frequencies below about 1500 wave numbers are coupled. So you almost never see a pure carbon-carbon single bond stretch. You almost never see a pure carbon-fluorine single bond stretch because they combine with other carbon-carbon single bond stretches or maybe with carbon to oxygen single bond stretches. So these can get to be quite complicated. Probably on Friday, I'll have the opportunity to show you all the vibrations of a fairly moderate-sized organic molecule, so you can see what all of these vibrations look like. Okay, but for our purposes now, and to continue on this functional group frequency business, I took this out of a book, a range of infrared group frequencies for some organic compounds. So up here you can see CH stretches, OH stretches like you'd have in water, NH stretches down here, and so on. SH stretches falling down. This doesn't show my SIHs, I guess. Here are carbon-carbon triple bonds like you'd have in acetylene, carbon-nitrogen triple bonds, and then carbon-carbon double bonds and so on. But when you get to these lower frequencies, notice, for example, carbon-carbon single bonds can range from about 700 up to about 1100 wave numbers. So that's certainly not a way of identifying you have a carbon-carbon single bond. So these wind up with a lot of coupling. But whenever you have frequencies up here, you can pretty well tell what's going on. The first graduate student I ever had was already employed at Dow Chemical. And in order to get promoted, he needed to get a master's degree. And so uh, I had him quickly do some computer calculations, and he wrote up a thesis and he got a degree. But this guy was a total whiz at looking at many organic compounds and say, this is an aziridine, and I can tell these bonds are stronger and weaker. And even though he didn't understand much about force constants before he did his master's, he became brilliant at looking at information like this. If you go to the library, you can find books of 500 to 1,000 pages just telling you what to expect for vibrational spectra, whether you have 135 substituted benzenes, 124 substituted benzenes, parabenzenes, et cetera, et cetera. So there's tons and tons and tons of empirical data uh, that we have for these systems. Okay, someone is reminding me to tell you all, we do have class tomorrow. Tomorrow is Friday, believe it or not, as far as classes go. So I think you all probably looked at your calendars, but we will also meet tomorrow. But we have 5 more minutes to go today, so let me continue on this page too. Here's a bunch of inorganic things. And over the years, I've also collaborated with some soil chemists in College of Agriculture and Life Sciences. And they obviously may want to know whether they have sulfates or nitrates or isocyanides or phosphates in the soil. And these are fairly easily defined. They're quite symmetrical molecules, so they don't have a lot of unique vibrations, or they're unique vibrations, but there aren't many of them and they're well defined. So you can see that you can get this information here. Here's another range of inorganic functional group materials, but when you see these values are really over a huge range, then you can't necessarily tell exactly what it is that you're looking at. But if you think you have a phosphorus oxygen bond and you have no bands in this region, for example, then you have to worry about did you make the right molecule. So most of you have already learned this from organic chemistry. The traditional ways of identifying molecules are infrared spectroscopy and NMR spectroscopy. And usually between the two of those, perhaps an elemental analysis that will tell you the percent of carbon, percent of oxygen, percent of nitrogen that you might have in a particular molecule. You can figure out what the entire molecule comes out to be. Okay, so we have 4 minutes left. We will take a look at just one simple molecule before we stop today. And so let's look at the vibrations of water. Water has 3 atoms, so 3n minus 6 is 3. These are the 3 vibrations. You don't need to pay attention to the A1, B1 symbols. Those are symmetry designations of what the vibrations are. A1 actually says that this motion is the most symmetric motion you can have. So one of the vibrations of water is called a symmetric stretch, and it comes at 3652 wave numbers. That comes out to be about 10 to the 14th times per second. There's another OH stretching vibration, and this is called the anti-symmetric stretch. So right now, let me point this out in case you didn't get this in organic chemistry. IR spectroscopy is very different from NMR. If we took the NMR of water, the NMR would tell us the 2 hydrogen atoms are equivalent, and we get a single signal for the chemical shift in the NMR spectrum. In infrared spectra, we have 2 equivalent hydrogen atoms, but they interact to give us a symmetric vibration or an anti-symmetric vibration, and they have 2 different frequencies. The third vibration for water, we don't have another bond stretching, it's the angle bending, and it looks like this, and it's at 1595 Reynolds. All of these band absorptions are huge and strong, so it's virtually impossible, not quite impossible in some regions, but virtually impossible to take infrared spectra of water solutions, because these huge, huge bands wipe out most of the spectrum that you would have from the molecules that are dissolved in water. Raman spectra, it turns out, have very weak water bands. And so the water is not going to interfere much at all. And many, many studies can be done in aqueous solutions. A lot of biological systems can be done by Raman that cannot be done by infrared. Okay, so how do we know what these vibrations are? You can do it two different ways. The way that we've been talking about all semester is you solve the Schrodinger equation. You have to write the potential energy function for this. And I don't have time today, but we'll look at it next time. And the other, you can treat it as classical physics, as having just connections of springs here, and you solve the equation of motion. When you get to larger and larger systems, you're much, much better off using the Schrodinger equation. And nowadays we have very nice computer programs that can predict these frequencies very accurately. So on Friday, this is where we'll continue. We'll look to see why this is the potential energy function for the water molecule. And then we'll look at some larger systems, and I'll try to give you a flavor of what those spectra look like. Okay, we have another chat question. Oh, sorry. Yes, thank you, thank you. No class Friday, we have class tomorrow, exclamation point. The test, I think, is a week from Monday. I hope somebody's checked that. I think I checked the syllabus, and it's scheduled for a week from Monday. So someone said, yes, it is, but it's yes, it is Monday, right? Can someone chat me? Yes, it is Monday. Okay, but not Friday. Okay. All right, so you now have a lot of problems to practice on for diatomic molecules. I wouldn't be surprised if up to half the next test is going to have to do with rotations and vibrations of diatomic molecules. So make sure that you understand how to get force constants, how to get bond distances, figure out what the spectra are going to look like, and things of that type. Okay, see you tomorrow. The next exam is a week from Monday.